Welcome to Pedagogy YouTube channel. Students, you can get different video tutorial of operating system, DBMS, networking, languages like Java, Python, etc. conducted by Manoj sir. We are going to discuss the critical section problem in operating system. Critical section problem, suppose we consider here 5 processes and the shared memory considered in the middle diagram. Now suppose P1 wants to get the shared memory and at the same time another process want to share the same memory. So there are so many processes, but only one process can access the shared memory at a time. Otherwise, there will be a race condition. Already we have discussed in this in our previous slide. Now consider this diagram. Suppose a typical process Pi, it may be P1, P2, P3, P4, P5, any process. Now, here in the do while loop, we fit that there is the entry section and another is the main part exit section. Now, suppose P3 wants to share or occupy the shared memory. It may be shared memory, it may be shared file, it may be shared devices, any shared properties, any shared item from the CPU, any shared data. Now what will happen? Whenever P3 want to enter, again P1 suppose demand the same shared memory from the shared memory location or shared data. Now what will happen? Whenever P3 access the data, no process are allowed to access that data. So we have to maintain some precaution. So whenever P3 will be in the shared memory portion, then the entry section, in the entry section, we have to fit a control. So whenever P3 completes its task, then P1 can enter into entry section and share the shared memory. At that time P3 exit. So again suppose P5 wants to enter. So P5 can access whenever P1 will exit. Until and unless P1 completes this task, P5 will have to wait in the ready queue. So for solve this critical section problem, we use Peterson algorithm and Semaphore. Semaphore, we are discussing here Semaphore, and next we will discuss Peterson algorithm. In Semaphore, there is a variable S and there is two functions, wait and signal. While Semaphore S equals to 0, that means there is no operation. And in signals, within the signal, S plus plus, S is the variable, integer variable, the Semaphore variable incremented, it means the function, the value, the variable within the signal function. And in the wait function, S is minus minus. So if we consider our previous example, suppose we initialize S equals to 1. Remaining portions are same. Within the do while loop, there is a wait part and there is a signal part. So S is equal to 1. Suppose P5 is the first process which want to share the shared memory. Now whenever P5 enter into the critical section, that means whenever the P5 will share the shared memory, then we have to initialize s equals to 0. P5 have to initialize s equals to 0. That means some process are executing, some process is executing in the critical section. So s is equal to 0, P5 shared the data, and whenever P5 completes its task, it has to send a signal that I have completed my task and another process can enter. Now at the time P1 enter into the P1 ready queue, P3 also enter into the ready queue, but until and unless s equals to 1, no process will be allowed in the critical section. Now look at the diagram. First P1 requires the same resource and second P3 requires the same resource, but P1 and P3 both are in ready queue. Whenever P5 exits from the critical section, that means it again set s equals to 1. That means P5 have completed its execution from the critical section. Now which one will get chance? In the ready queue there are two processes, so P1 will get chance because it is in the first. So this is semaphore by which we can